right, everyone. So why do we explore? I would say there are probably a million justifications. But isn't it fundamentally because we find it irresistible, the idea of going to a place where no one else has ever been? I think it's just we can't help ourselves. We have to explore. And a great example of this is just over 200 years ago, a Russian ship spotted Antarctica, the last giant, I know, right? Woo! This is not an enticing place. This is not a rewarding place. You don't go there for the business opportunities. But the race to the pole was on. And it led to this, which I think is the most heartbreaking image in all of exploration. It's the moment in 1911 when Scott's team reached the South Pole and found waiting for them Amundsen's tent, with a letter to Scott in the tent saying, "We beat you," basically. And then famously, and tragically, Scott's team whole died on the way back to their base camp. But this is the kind of drive that we humans have to explore. And so in the time since the South Pole race, we've sent robotic and crewed expeditions to our beautiful rocky neighbor, the moon. This is the Orientali Impact Basin. It's on the limb of the moon. You can't see it from the Earth. It took the Ranger mission to take this picture. Giant impact into this rocky surface filled now with a black basalt pool. We have an entire fleet of robots looking at Mars for us. And this is Burns Cliff on Mars. It's named after Roger Burns, who's a mineralogist who posited what minerals we might finally find on the surface of Mars, and he did so correctly. And when I was an undergraduate, I took every course that he ever offered, and he was a lovely human, and I'm really glad he has this named after him. And of course, we've sent flybys and orbiters to beautiful Jupiter here, giant gas-rich planet, and to the icy outer moons, and flybys to the icy moons themselves. So where am I going with this? What's a kind of body that we've never explored? How about a body made mostly of metal? And that's what we think this asteroid is, asteroid 16 Psyche. We think that it is largely made of metal and that it has a metallic surface. So this is primary fundamental exploration, a kind of body that humans have never even taken a picture of. Here's another impression. This is an artist's impression, like the last one, of the surface of Psyche. These beautiful pieces of art that I'm showing you are created by a very talented artist named Peter Rubin. He's done things like designed one of the S's for Superman and worked on Ghostbusters and stuff. And he and I would Zoom on the weekends for like 2 years while I downloaded into his brain all the science that we thought about this, and he converted it into art. And I'm pointing this out especially because we really don't know what Psyche looks like. But you got to tell the story. You got to get people excited to go to a place that we don't know what it looks like. So we have a number of firsts on our mission, designing a mission to go to an unknown body. Think about that from a science point of view. How are we going to do our hypothesis testing? What hypothesis do we have? And how could we possibly make sure we fly the right instrument suite? So I'll be talking about that later. So first metal surface body that humans have ever visited. First time Maxar was a prime contractor for NASA on a deep space mission. First Hall thrusters outside of Earth-Moon orbit. I'll show you some pictures of those. So a question that I get very often is, how old were you when you knew you wanted to work on a NASA mission? And the answer is like today years old, because this is me at age 7 riding Barney, who was great. I was completely obsessed with horses and dogs. I rode competitively for years. But I might be a little bit the exception, because when I give public talks, sometimes I ask the people who come who are all interested in space, how were you, what was the moment for you? How did you get interested? And usually about a third of the people say, and I'm about to take a poll, I saw Saturn through a telescope when I was 10, 11, or 12 years old, and it changed my life. Is that true for anybody here? Some number, not a third. Interesting. Anomalies. Okay. Well, I saw Saturn, but I still wanted to be a veterinarian. And here I am in my doctoral robes, just stepping off faculty for another position and giving my son a hug. And so plenty of tech spirit. But in the end, the thing that really brought me to the NASA mission and to trying to discover what this asteroid is a love of teams. I think teams are the miracle and also sometimes the tragedy of humanity. This is just a little part of our team. At peak, we are at 800. We've had over 2,000 people work on this project. It's a big project. The budget's over $1 billion. And so for me, it's about the team. How do you make something so complex that no single person understands how it works? That is a miracle of human evolution, that we can now do that. How do you forge a team who's very functioning, creates an improved product? And we have a motto on Psyche that the best news is bad news brought early, because that's when you can take action. So we want to make sure that every voice is heard, especially the voices of the people who have the authentic boots on the ground knowledge of what is actually happening, as opposed to what happens when that message is diluted or changed through playing telephone through many layers of the organization. You need the authentic information. So I just want to make this clear. This little part is foreshadowing. Okay, got that? Yeah. All right, important to remember that despite the lovely artist renditions, we do not know what Psyche looks like. This is a telescope picture of Psyche from my backyard in 2017. Did you just spot it? That was it? Yep. Some of you might have spotted it. It's a little clearer than the other stars. And of course, asteroid means star-like. And it's not much bigger and brighter in the 60-inch in Mount Wilson, and even in Hubble, it's just 4 pixels. So it's far away. Here's the closest we have to an actual image of Psyche. These are not photographs, these are shape models created by watching how radiation reflected off of Psyche as it spins on its axis comes back to the Earth and changes over time during its 4-hour and a little bit day, Psyche's spin. And so these were created by it comes out of a paper, Shepard et al. 2021. They used radar from Arecibo, rest in peace. Radar from Arecibo has been very important to us in Psyche. The Atacama Large Millimeter Array, adaptive optics from Keck on Mauna Kea, and also the Very Large Telescope in Chile, and also occultations from astronomers all over the world watching Psyche move in front of stars. And with all of those inputs, they create these shape models. And you can see that Shepard's effort in 2017 and 2021 are fairly similar and not that dissimilar from Ferret et al. 2020, but there are other really good teams that have made shape models that are not as similar as these. And so we have a vague idea of the shape of Psyche. I say shaped like a potato because that is really brings it, there are a lot of things that are shaped like potatoes, so we're not wrong. it's absolutely shaped like a potato. So as asteroids go, Psyche is a big one. It contains about 1% of the mass of the asteroid belt, even though the asteroid belt has between 1 and 2 million asteroids. And so I like to show it compared to Arizona, where I live now, and also Massachusetts, where I spent most of my life. It's the size of Massachusetts without the Cape, so that's like a rule of thumb for Psyche. And I didn't drop it right on Ojai, but just to give you an idea, the area of the surface of Psyche is about the same as the area of California. And so when we get to Psyche with our beautiful robotic spacecraft, we'll be orbiting for 26 months. It's an orbiter, trying to investigate something the size of California. So that's, I think, a way that I find helpful to think about how complex this is going to be. So where is Psyche? It's really, really far away. So here's our solar system from the Sun to Jupiter. And this is where Psyche orbits in the outer main asteroid belt. And so some context. So from the Earth to the Sun is an astronomical unit. That's about 150 million kilometers. When Psyche is at its farthest, when it's on the other side of the Sun from the Earth, it can be 650 million kilometers away from us. And when it's the closest it can be, when it's on the same side of the Sun as us, it could be only 250 million kilometers away. So is that far or near? Well, for comparison, Mars gets as close as 55 million kilometers, so 3 times closer. So Mars is like in our backyard compared to Psyche. What is the point? The point is, Psyche is never going to make us rich. That's the point. I don't know if some of you have seen these headlines. I just got a Google alert just now that another one came in, Psyche is going to make everyone on Earth a billionaire, or whatever it is. The number of dollars of the purported value of this metal object is irresistible, even to Forbes and the Smithsonian. So they're great headlines, but there is zero truth involved, and so feel free to spread that to your friends. Psyche is never going to hit the Earth, and Psyche is never going to be brought to the Earth. So that's the key thing. So you know who really got it right was the Miami Herald, actually. They really tried hard. So asteroid Psyche won't make you rich or hit the Earth, but NASA has another reason to visit it, which is the fundamental science of building habitable rocky planets. And so think about the very beginning of our solar system. When I teach planetary science, I always tell my students, there's one number you have to memorize, and if you don't memorize it, you fail. And this is the number. Are you ready? 4.568 billion years ago. That's when the first solids formed in our solar system. That's the age of our solar system, 4.568 billion years ago. So within 1.5 million years out of that 4,568 million years, bodies called planetesimals formed. They almost look like miniature planets, we think, the size of cities or the size of continents, and some of them heated up from the short-lived radioisotope aluminum-26 and melted. So the material that was in this disk and forming these planetesimals was rock and metal intimately mixed on a millimeter centimeter scale. But when they heat up and melt, the metal, which is twice as dense as the rock, sinks to the middle and forms a metal core. That's what we have on our Earth, and Venus, and Mars, and the Moon, and Mercury all have metal cores in their middle, so the same structure as this. This is how we think that Psyche started. Later on the lawn, if you come by, you can hold a piece of metal meteorite that might be what Psyche's made of, and it is 4.568 billion years old. So how do you get to an object that's mostly metal or has a metal surface from this? Well, this is our idea. Impactor knocks the rock off. The liquid metal core freezes from the outside, creates a beautiful magnetic field, erupts sulfur volcanoes, and eventually, by the impacts, gets tipped over on its side until it becomes the Psyche of today. This is a really interesting problem, to try to design a mission to go test this hypothesis. This is a situation where Occam's razor is really hard to use. And a good reminder for us is that William of Ockham wanted us to choose the simplest process, not because it was most likely to be correct, but because it was the easiest to test. And so that is our simplest hypothesis, but it's not even quite as simple as that, because we think it would take 8 to 11 impacts to strip the rock off and leave the metal behind. Still, it's our best idea. So that's our top objective for the mission. Discover whether Psyche is in fact a metal core of a planetesimal that was knocked into pieces, spin axis knocked over into the plane of its orbit like a rotisserie chicken and stranded in the asteroid belt, or could it be something else? What are some of the ways that we could learn about Psyche here from Earth to get ready for this mission? One is to compare its reflected light spectra to the reflected light from meteorites. There are about 70,000 meteorites on Earth that have been collected by people, largely in North Africa and in Antarctica. But meteorites, you may know, are almost all recent arrivals from the asteroid belt. There are just a few that come from Mars, there are a few from the Moon, some unknown. Almost every one was recently knocked off an asteroid. So they're really a library of compositions of the asteroid belt. So we compare Psyche's reflected light spectra to these. These beautiful ones, I know that a lot of you know, are called pallasites. The silvery part is iron nickel metal. That's what we think the metal on Psyche is. And the other parts are silicate minerals that just shine, which is beautiful. But they don't even match the spectra as well as they might. The meteorites that match the spectra the best are CB chondrites. And if you are a meteorite aficionado, you'll be going, that's strange. These are very strange, rare meteorites. And you can see the one on the left. See how the gray balls of iron nickel metal, they really were apparently melted droplets. They were droplets of metal stuck together by weird silicate minerals. And the leading hypothesis for their formation is that they are the frothy result of a giant impact early in the solar system. So could you make froth from an impact the size of Psyche, the size of Massachusetts? That would be quite an impact, much bigger than the little cartoon one that I just showed you. We don't know, but it would be really amazing if Psyche turned out to be made of CB chondrites. That would be pretty great. So another one of our big questions about Psyche is, what does its surface look like? So I showed you the pictures of the Moon and Mars and of Jupiter, but we haven't seen a metal surface before. So we have the question, what would an impact into metal look like? So we've done these in the lab. This is a hypervelocity impact, and that little ball is not the impactor that made the crater, because of course that guy is gone. This is just another one to show the size of it. But look at this amazing cup-shaped fluidized crater. That's what happens with the shock of a hypervelocity impact. Actually fluidizes the material, and it behaves as if it were a droplet in milk or some other kind of liquid. and see the ejecta flap sticking out at the top. If this was in rock or ice kinds of impact craters we have seen, those ejecta flaps just fall back down on the surface. But with metal, they froze before they could fall. So could Psyche's surface be covered with little pointy teacup, horrible things you wouldn't want to walk on with the beautiful robots that you all are building? So that's one of the things that we want to see if we can discover. All right, how does a NASA mission like this come to be? And the answer is, we won a humongous 3-year competition to fly. And it started way back in 2011, actually. That's how long I've been working on this mission, with an invitation from a couple of scientists from Jet Propulsion Laboratory to see if we could design a mission that would test the hypothesis of a science paper I'd written. It's kind of exciting when more than 5 people read your paper and they're not even your top competitors. Like, these people, it was like amazing. It was pretty great to get that email, and the answer to that is, of course, yes. Let's talk about designing a mission, yes. So 3 years later, this is the cover of our Step 1 proposal, also work by Peter Rubin. And you can see now, you understand what this is a picture of. This is a picture of 2 planetesimals striking each other. We're trying to tell the story. Imagine that you were writing a proposal for a space mission, and you wanted to go to Mars. People immediately have a mental image of what we're talking about. And like, we've seen Matt Damon there. We know what it's like to go to Mars. We can do that. And we didn't have that advantage. We had to convince the people who are reading our proposal that they would be very interested in an asteroid that many of them had never heard of and that no one had ever seen. And so we had to create in their heads the video reel that we as scientists were seeing, the cartoon that I showed you just now of the impact and the rock stripping and the metal. So this Step 1 proposal took 50 people to write, and it was 218 pages long. 28 proposals were submitted, and 5 were down-selected to go on to Step 2. And I was so surprised to be down-selected. You don't usually get selected the first time through this process. That's usually a multi-decade process that usually ends in not ever being selected. And so that's what we were ready for. It's a very interesting emotional journey to prepare yourself for that phone call. And so we were one of 5 that were down-selected. And here's our Step 2 proposal showing that same impact about 30 seconds later. And you can see the red molten metal core of the planetesimal being revealed from underneath the streamers of rock that are being struck off. And Peter said this was one of his favorite pieces of art he'd ever done. And we love it too. And so you can see we're still trying to tell that story, This is called a concept study report. It was 1,053 pages long, and it took 150 people to write. And to my intense surprise, and in a moment that did change my life forever, in January of 2017, Thomas Zurbuchen called me up, he's here, called me up and said, "We've selected you for flight." And off we went, 2017. So let's look at our spacecraft. All right, we have this model here, but I don't want you for a moment to think that this is a $1 billion project. This is these beautiful 20 kilowatt solar arrays built by Maxar will unfold after we launch. And when they unfold in real life, they're 25 meters across. So this hall is 18 meters side to side. So when our spacecraft unfolds its beautiful solar arrays, it would need 7 more meters of space to even unfold across this hall. So that gives you a sense. It's the size of a singles tennis court. So these beautiful 20 kilowatt solar arrays, now we're going out to Psyche. And as you all know, flux has a 1 over r squared relationship with its source. So when we go from 1 AU at Earth to say 3.2 AUs at Psyche, 1 over 3.2 is about 1 over 10. So we'll get 1/10 of the power when we're out there. So we'll only get 2 kilowatts to run everything. So what are we going to be running? We're going to be running our science instruments that are up here. This one over here is the gamma ray and neutron spectrometer, which through some miracles of physics and the creation of intergalactic cosmic rays in other galaxies will allow us to measure the surface composition of the asteroid from orbit. And this is built at Applied Physics Laboratory. These guys are 2 magnetometers in a gradiometer configuration, one above the other, so we can subtract the magnetic fields of the spacecraft. They're built by Danish Technical University in Copenhagen. These are our imagers right here. They are multispectral imagers, so we'll be sending back both color pictures but also slices at certain wavelengths so that we can identify surface compositions. And we've already built the data pipeline for that imager suite such that those pictures are going to come on the internet within 30 minutes of our receiving them from the Deep Space Network without our editing. So we're going to share everything with the world all at once because I think that's what space exploration is for, and we can all be scratching our head at the same time, as Jim Bell says, wondering what are we seeing. I will also point out over here, this is the Deep Space Optical Comm DSOC. That is a tech demo. It's not part of our science mission. It's a tech demo for NASA to practice communicating back and forth between Earth and the spacecraft using lasers instead of radio waves, because you can encode a lot more information in lasers. So we joke that this is how we're eventually going to stream Netflix to Mars, is with the children of this instrument right here. And it is a tech person's dream. I'm just going to say superconducting nanowires, which I think is just like the coolest thing ever. And these are our SPT-140 Hall effect thrusters, which I'm going to show you some photos of in a minute. And then finally, our high gain antenna up on the top. And inside that spacecraft is a huge tank of xenon, because that's our propellant. So, all right. But wait, we were supposed to launch last August, and we did not. We did not quite make it through COVID. We actually completed a fully functional whole spacecraft and delivered it to Kennedy. And there were some things that were just not quite done, and one of them was testing the guidance, navigation, and control software. You don't not really want to launch unless your guidance, navigation, and control is primo, then you're really confident about it. A launch slip of this magnitude is really deeply disappointing, and it's painful for the team, and it's extremely expensive for taxpayers, and we all wish that we had different kinds of medication like lidocaine around all the time just to help us through this. But here's the lesson, and this is what I was sort of foreshadowing by telling you that I care so much about the culture of teams. A contributor to our slip was a failure in culture in one part of our team where their distress and need for resources was not transmitted with high fidelity up to the leadership so that we could really help them in time. And so the slip is really validation that team culture is critical, not just for ethical reasons, and not just for daily functioning, but literally for overall success, for risk reduction, and even for budget. So that is a huge and interesting lesson that I've learned through this process. So, but now, we have been approved for launch in October of this year. And so October 5th of this year, at 10 o'clock in the morning, Florida time, God willing, we're going to be launching. And so what we'll do is we'll launch off of the Earth, and we'll go to do a Mars gravity assist, and we'll make it all the way out to Psyche capture 5.8 years later. Stand by, it's going to happen. And then we will orbit for 26 months and find out what this thing is. So when the spacecraft arrives at Psyche, we'll start in a faraway orbit, orbit A, then we'll step down to orbit B, we'll step down to orbit C, and eventually we'll do a plane change maneuver and end up in orbit D, where we'll get that surface composition in the end. Why do we have to do this? We have to do this because we do not know its shape or mass or compositional distribution, so we don't know its gravity field. And you can't calculate a stable orbit until you know the gravity field. So we'll do the gravity field as best we can at this high orbit, then we'll step down to another stable orbit, do a better determination, step down. We'll get the gravity field to about degree in order 10. But if you need a little more kind of like gut feel for what this would be, imagine that beautiful potato where one end of it is made entirely of metal at 7,000 kilograms per cubic meter, and the other half is entirely of rock at 3,000 kilograms per cubic meter. You can have a very strange gravity field. So we'll be ready for that. We've run Monte Carlo simulations, like 5,000 Monte Carlo simulations, to make sure we can always find a stable orbit D. So that's the plan. All right, let's look at a little bit of hardware before we say goodbye. This is a shipping container for a big spacecraft, and I know some of you know these very well, and for others it might be fun to see, like it has been for me. It's basically a mobile clean room, because the spacecraft is built under very clean conditions, and it gets held by its adapter ring up within this mobile clean room, which is fully instrumented, so we know exactly the temperature, exactly the shock, everything that the spacecraft experiences, and it's got 2 generators. In case one fails, the other one will keep going. So I was nonetheless quite nervous when it was shipped in this from Maxar in the Bay Area down to Jet Propulsion Laboratory for assembly and integration. And there is a stencil on the side of this which says, "Spaceflight hardware do not drop." And I just would look at this and go like, how would that happen? I don't even, and how would you not know what was, well, anyway, yeah. Yeah, just my ignorance that that could possibly be needed. This is me on the right, and Henry Stone, our project manager in the clean high bay at Jet Propulsion Laboratory. You can see, even only just seeing our eyes, how thrilled we are to have this. It's amazing to work on something for 10 years, and I know some of you have had much longer spans, but 10 years was good for me, and then see it become manifest. Like, you can't even believe your eyes. You've been looking at pictures of it so long, you think the pictures are real. And this is the DSOC team, having just installed the Deep Space Optical Comm. Proud of their incredible instrument that they're doing. Here's just a hero shot from 2021 in the JPL high bay, clean high bay. All right, thrusters. See these beautiful thrusters here with their white arm? The arm has an elbow and a shoulder, so you can move the thrusters in any way that you want relative to the spacecraft, and they have their red remove before flight caps on them. But here's what they actually look like. And you can see they're about the size of dinner plates. They're not that big. So on the right is what a picture up close, and on the left is in the thermal chamber at JPL being tested. So the propellant is the noble gas xenon. And what happens with these ion thrusters, with the Hall effect thrusters, is the xenon gets ionized and then sent through a potential field, and it's the momentum of those tiny xenon atoms, just milligrams per second generally, that actually push the spacecraft forward. And xenon ionizes blue. I think it's gorgeous. This is really what it's going to look like in space, even though we won't be seeing that, unfortunately. And the result is a thrust that's just measured in millinewtons. It's very, very efficient, though. So it's what allows us to go to the outer main belt on a Discovery-class mission. Here I am on the left next to Brian Bone, who's our assembly, test, and launch operations manager. And we're looking up at the comms panel that had just been installed. We've been having some challenges with our SDSTs, for those of you whom that acronym means anything. And I was very excited to see it working on the spacecraft. So let's see. Oh yeah, so the next thing that happens is we had to do environmental tests. And so you have to test for electronic compatibility or interference. And to do that, you have to exclude all of the other fields that exist in a plethora around the clean room at JPL. And so you need a Faraday cage. So this is a Faraday cage the size for a giant spacecraft made of conductive carbon fiber material. We put the whole spacecraft in there, and then it would just be measuring its own electric fields and magnetic fields and how they interacted. Past that with flying colors, I was happy to say. Then it goes into the thermal vac chamber. And so this is one of JPL's, or maybe the biggest at JPL, I'm not sure, thermovac chamber. You see the 2 people for scale. And that silver thing, that's the adapter ring on the bottom of our spacecraft going into that chamber, which is 25 feet in diameter. Then a big door comes and closes, and then it becomes evacuated and cooled down to very cold. And there are lights on the top, so it can have like a sun side and a cold side. And that's when you find out how good your thermal models are. And we found a bunch of things we needed to fix and adjust with our thermal models. And I gather the thermal models for a spacecraft are quite difficult. They're a constant challenge. I think mostly because the interfaces between parts of the spacecraft are not always perfect conductors, and you don't know how non-conductive they are, so it makes it very difficult. So keeping this cold also is quite a challenge. It takes a lot of liquid nitrogen, and we're just tanker trucks going into JPL one after the other all day while we were running these tests. We did very well, learned some good things. And here we are testing the solar arrays. You have to offload gravity because they're really designed only to unfold in space. So with this particular scaffolding, offloading the gravity, we can only do the big bar in the middle. We can't do the cross pieces. They have to be done even with a different set of scaffolds to protect them. But aren't they beautiful, those big solar arrays? And then we shipped it on a C-17 to Kennedy. And here it is coming off of the plane, and it occurred to me during the practices of this talk that maybe this is where you don't drop it. Maybe that's it. Maybe that's the moment. So we did have to take our shipping container and test it at March Air Force Base and make sure it actually fit in the C-17, because that's the biggest transport plane you get for these things. And it's just inches to spare, just inches to spare. But what a beautiful piece of technology that is. And so finally, I want to share with you a really amazing thing that would seem to only happen here at Mars. Yesterday, we all heard this amazing panel about the James Webb Space Telescope. And if we didn't know her ahead of time, we met Sarah Kendrew, who is a major part of the MIRI, mid-infrared instrument. Well, I'd never met Sarah before. I didn't know she was involved with the instrument, but 7 days ago, her instrument looked at my asteroid, which I think is really cool. I think that's just kind of perfect Mars. So this is basically uncalibrated, unprocessed spectrometer data for the asteroid. And we're looking from 5.7 to 6.6 microns here, looking for evidence that there's hydroxyl or water bound into crystals on the surface of Psyche. And this is a measurement you cannot do from the Earth's surface because the atmosphere interferes. You can only do it from James Webb or gorgeous things like that. So it's so lovely to meet Sarah and to be able to share all of this with you today. And so please keep your fingers crossed. God willing, October 5th, 10 a.m. Go Psyche. Thanks a lot.